Our universe thrives on rhythm. This rhythm is not just a poetic notion, but a fundamental aspect of nature. From the smallest atom to the largest galaxy, a constant dance of motion governs the cosmos. These movements are not random, they follow specific patterns and cycles. This dance, known as oscillation, is simply the repetitive back and forth movement of an object around a central point. Oscillations can be found in various forms and scales. Think of a pendulum swinging, a guitar string vibrating, or even the ebb and flow of tides. These are all examples of oscillatory motion. The ebb and flow of tides are driven by the gravitational pull of the moon and the sun, creating a rhythmic pattern in the oceans. Oscillations are fundamental to our understanding of the physical world. They are present in mechanical systems like the gears of a clock and in natural phenomena like the changing of day and night. They shape our experiences, from the gentle rocking of a cradle, which soothes a baby to sleep, to the rhythmic patterns we observe in our daily lives. Oscillations are also crucial in the realm of sound. The vibrations of a speaker create sound waves that travel through the air, reaching our ears and allowing us to hear music, speech, and other sounds. By unraveling the principles of oscillations, we unlock a deeper understanding of the universe's intricate workings. Scientists study these principles to develop technologies and solve complex problems. Whether it's the gentle swaying of trees in the wind or the complex vibrations of atoms, oscillations are everywhere. They are a testament to the interconnectedness of all things. The complex vibrations of atoms form the basis of many physical properties and behaviors of materials. Understanding these vibrations helps us in fields ranging from material science to quantum physics. Join us as we embark on a journey to explore this fundamental phenomenon, unraveling its secrets and appreciating its profound impact on our world. Through this exploration, we gain a greater appreciation for the rhythmic nature of the universe. Imagine a spring stretched and released. It bounces back and forth, a perfect example of simple harmonic motion, or SHM. In SHM, an object's restoring force is proportional to its displacement from equilibrium. This means the further the spring is stretched, the stronger the force pulling it back. This elegant dance of force and displacement creates a predictable pattern of motion. The time taken for one complete cycle, like the spring returning to its starting point, is the period. The frequency, on the other hand, tells us how many cycles occur per second. SHM is not just limited to springs. It governs the swing of a pendulum, the vibrations of a tuning fork, and even the oscillations of electrons in an atom. Understanding SHM unlocks a fundamental principle governing motion in our universe. Imagine pushing a child on a swing. Without your gentle nudges, the swing's motion will eventually slow and stop. This natural decay of oscillations is called damping. It occurs due to frictional forces like air resistance, converting kinetic energy into heat and reducing the amplitude of oscillations over time. Damping can manifest in various forms. Over-damping, like pushing the swing too slowly, results in a slow return to equilibrium without any oscillation. Under-damping, like a gentle push, allows for oscillations but with a gradually decreasing amplitude. Then there's critical damping, the perfect balance where the system returns to equilibrium in the shortest time without oscillating. This principle finds its use in car shock absorbers, ensuring a smooth ride by quickly damping out any bouncing motion. A swinging pendulum left to its own devices will eventually come to rest. This gradual decline in motion signifies a loss of energy. In damped oscillations, energy isn't lost instantly but dissipates gradually over time due to friction. As the oscillator moves, it encounters resistance from air molecules or internal friction within the system. This resistance converts kinetic energy, the energy of motion, into heat, effectively slowing down the oscillations. The rate of energy decay depends on the type and strength of damping. A heavily damped system will lose energy quickly, while a lightly damped one will dissipate energy slowly, allowing the oscillations to persist for a longer duration. Section 5. The measure of harmony, understanding the quality factor. Imagine two bells struck with the same force. One bell rings with a clear, prolonged tone, resonating beautifully in the air. The sound lingers, creating a sense of harmony and continuity. Meanwhile, the other bell produces a dull thud that quickly fades away, leaving a sense of abruptness and incompleteness. This stark difference in sound quality can be quantified using a parameter known as the quality factor, or Q factor. In essence, the Q factor measures how well an oscillator, such as a bell or a spring, can sustain its energy over time. A high Q factor indicates low energy loss and sharp resonance, resulting in a long-lasting, pure tone that can be both heard and felt. Conversely, a low Q factor implies significant energy dissipation, leading to a quickly dampened, less resonant sound that fades away rapidly. The Q factor is crucial in various applications, from scientific research to everyday technology. It plays a vital role in designing musical instruments with specific tonal qualities, ensuring that each note is clear and sustained. Additionally, it is essential in optimizing radio receivers for precise frequency selection, allowing for clear and uninterrupted communication. Understanding the Q factor helps us control the efficiency and precision of various oscillating systems, from mechanical to electronic, enhancing their performance and reliability. Section 6, Nature's push and pull, delving into forced oscillations. Imagine pushing a swing at just the right moment, adding a little extra energy with each push. This rhythmic input of energy is the essence of forced oscillations. Instead of relying solely on its natural frequency, the system responds to an external periodic force. This external force can amplify or dampen the oscillations depending on its frequency. When the driving frequency matches the system's natural frequency, a phenomenon called resonance occurs, leading to maximum energy transfer and large amplitude oscillations. Forced oscillations are everywhere. They explain the vibrations of a bridge under the rhythmic steps of marching soldiers, the operation of a microwave oven heating food by exciting water molecules, and even the behavior of our eardrums responding to sound waves. Section 7. Finding balance, steady-state motion in forced damped oscillations. Imagine a swing set in motion by a constant rhythmic push. Initially, the swing's movement might seem erratic, but eventually it settles into a consistent back-and-forth motion with a fixed amplitude. This equilibrium state is known as steady-state motion. In forced damped oscillations, the system initially responds to both the external force and the damping force. However, over time, the damping force dissipates energy, causing the transient behavior to die down. Once the system reaches steady state, the energy input from the external force perfectly balances the energy dissipated through damping. This equilibrium results in a constant amplitude of oscillation, independent of the initial conditions. Section 8. A dance of interdependence, exploring coupled oscillations. Imagine two pendulums hanging from a common support, their swings subtly influencing each other. This interconnected motion exemplifies coupled oscillations, where two or more oscillators interact and exchange energy. This coupling can arise from various mechanisms, such as a physical connection like a spring or through shared energy fields. The behavior of coupled oscillators becomes a mesmerizing dance of interdependence, with energy transferring back and forth between the oscillators. Coupled oscillations are crucial in understanding a wide range of phenomena, from the synchronized flashing of fireflies to the complex interactions of atoms in a molecule. They highlight the interconnectedness of systems and the fascinating patterns that emerge from their interactions. Section 9. Oscillations, the unseen symphony orchestrating our world. From the rhythmic beating of our hearts, which tirelessly pumps life through our veins, to the vast expanse of the cosmos, where stars pulsate and galaxies rotate in a cosmic ballet, oscillations permeate every facet of our existence. They are present in the gentle sway of a pendulum, the rhythmic motion of ocean waves, and the vibrations of a spring. They are the unseen symphony, orchestrating the universe, creating harmony in the chaos, shaping our experiences and driving countless natural phenomena. From the ebb and flow of tides to the vibrations of a tuning fork, oscillations are at the heart of it all. Understanding oscillations unlocks a deeper appreciation for the intricate dance of energy and motion that governs our world. It reveals the hidden patterns that dictate the rhythm of life. It allows us to comprehend the workings of musical instruments, design earthquake-resistant buildings, and innovate in ways that enhance our daily lives, and even unravel the mysteries of the cosmos. Scientists and researchers delve into the oscillatory nature of stars and planets to understand the universe's grand design. As we continue to explore the fascinating world of oscillations, we find that they are fundamental to both technology and nature. We uncover new layers of complexity and beauty in the universe's grand symphony. Each discovery adds a note to the ever-evolving melody of existence. From the mundane to the extraordinary, oscillations are a constant reminder of the dynamic forces at play. Oscillations remind us that even in stillness there is constant motion, a subtle dance that keeps the world in balance, a testament to the dynamic nature of our universe. From the smallest atom to the grandest galaxy, oscillations are the heartbeat of existence.